So now let us consider one example on how to construct analytical function if real or imaginary part is given. So we have a function here, u is equals to x cos 2y minus y sin 2y is the real part of a given function. Then this equation I'm going to differentiate with respect to x partially and y partially. So what we are going to get, u subscript x. So with respect to x I am differentiating, so I have to keep this cos 2y as it is. Differentiation of x is going to be 1, so cos 2y minus, here we don't have any x term, so this differentiation is going to be 0. So what we are going to get, u subscript x is equals to cos 2y. And similarly if I go on differentiating this function with respect to y, u subscript y. So I have to keep this x as it is. Now I'm going to differentiate this cos 2y. Cos differentiation is going to be minus sin 2y, and again 2y differentiation is 2. Minus, and I have to apply u into v rule here, so y I'll keep as it is. Sin differentiation is cos 2y, again 2y differentiation is 2, plus this sin 2y I have to keep as it is. Y differentiation is going to be 1 with respect to y. So now if I simplify this, minus 2x sin 2y, minus 2y cos 2y, minus sin 2y. So this is what u subscript y we are getting. So this is equation, let's say 1, and this is equation 2. Now we have f dash of z is equals to u subscript x plus I into v subscript x. So this is what we have. So with the help of CR equations, what we have, ux is equals to vy and vx is equals to minus uy. As I told you, if real part is given, I have to consider this vy. So I mean, sorry, if u is given, I have to eliminate this vx, so I'm going to consider minus uy. So here ux we know already, plus I'll keep that because ux is known. I don't know vx, so but vx is equals to what we have here, minus uy. So I'm going to replace that, minus uy. So this is equals to, so here this is ux minus I uy. So this is f dash of z. Now ux and uy we know, we are going to substitute those two. That is f dash of z is equals to, ux is equals to what we have, cos 2y, minus vxi as it is. So uy is equals to what we have, minus 2x sin 2y minus 2y cos 2y, minus sin 2y. So this is what we are getting. So if I simplify this, so what we are going to get here, cos 2y, minus this is going to be plus I 2x sin 2y, minus plus I 2y cos 2y, minus plus I sin 2y. So this cos 2y and this, I can group the terms, or else what we can do here, with the help of Milne's Thomas method, what we can do, I can put x is equals to z and y is equals to 0 here. That is f dash of z is equals to, if I substitute 0 here, Okay, cos of 0 is going to be 1. Okay, plus if I substitute y is equals to 0, here in this case sine 0 is 0, this whole term is going to be 0, and here if I substitute y is equals to 0, again this whole term is going to be 0. If I substitute y is equals to 0, this whole term is going to be 0, so all other terms are going to be 0. Only thing what we are going to get, f dash of z is equals to 1 we are getting. Now we need f of z, because we are constructing analytic function. That is, for that purpose what we are going to do, we are going to integrate this. Okay, on integrating on integrating okay, so on integrating, so what we can do here, f dash of z with respect to z I am going to integrate, so this is 1 with respect to z plus integral constant c. So here this integration is going to be f of z. Okay, one integration with respect to z is z plus integral constant. So this is the required analytical function. Okay, thank you. Let us consider one more example. Here u is equals to e to the power x cos y. Again we have a real part, so we are going to differentiate u with respect to x partially. So e raised to x differentiation is e raised to x only, and cos y we have to keep as it is, that is cos y. Okay, and u again I am going to differentiate with respect to y. Uy is equals to e to the power x as it is I have to keep. Cos y differentiation is going to be minus sine y. So what we are getting, minus e raised to x sine y. So this is uy. Once after doing this, what we have to do, we have to write f dash of z is equals to u subscript x plus I into v subscript x. Again from CR equation, Vx is equals to what we have, minus Uy. Okay, so then what happens here, Ux minus I Uy we are going to get. So we know Ux is nothing but e to the power x cos y. Okay, minus I into, we know Uy minus e raised to x sine y. Okay, so if we simplify this, e raised to x cos y plus I e raised to x sine y. This is what we are going to get. Okay, so now we can solve this by two ways. What we can simplify directly this one. How we can simplify? Let me check. Let me show you here. So that is f dash of z is equals to e to the power x. I am going to take common. Okay, so what remains? Cos y plus I sine y. Okay, so e raised to x, so this one I can write it as e to the power iy. Okay, so e to the power iy means, if I bases are same, we have to add powers, so e to the power x plus iy I'm going to get. So that is f dash of z. So this is nothing but x plus iy is nothing but z, so e to the power z I am getting. So f dash of z is equals to e to the power z. If I integrate this, f dash of z is equals to e to the power z, integration is to the power z only, plus integral constant c. This is one how we can solve. Or else if I am going to use Milne-Thomson method, again from here what we are going to do, I have to substitute x is equals to z and y is equals to 0. So here f dash of z is equals to, if I substitute wherever x is there, if I substitute there z e to the power z, and wherever y is there I have to substitute 0. So cos of 0 is going to be 1 plus I e to the power z, sine of 0 is going to be 0. So what we are getting, e to the power z. So this term is going to be 0. Okay, so this is f dash of z. Again if I integrate this one, I'll get f of z is equals to e to the power z, integration is e to the power z plus integral constant c. So this is a required analytical function. So we can go by this way, or else using Milne-Thomson method also we can solve. But Milne-Thomson method is easy to solve compared to this arranging the terms. Thank you. Let me consider one more example. U is equals to cos x into cos hyperbolic y. Okay, so I'm going to differentiate this u with respect to x. So this term is going to be, cos x differentiation is minus sin x, and this cos hyperbolic y as it is I have to keep. and again I am going to differentiate with respect to y. Cos x I have to keep as it is. Cos hyperbolic differentiation is going to be sin hyperbolic y. Okay, then what we have to do, f dash of z is equals to u subscript x plus I into v subscript x. Okay, so again by CR equation what we are going to do, u subscript x minus I u subscript y we are going to write. Okay, so u subscript x means what we have, minus sin x into cos hyperbolic y minus I into u subscript y, what we have, cos x, this is sin hyperbolic y. So if I take minus sign common, what we are going to get here, sin x. So cos hyperbolic y, how can I rewrite, cos of I y, and this I along with sin hyperbolic, how can we rewrite, this is plus cos x as it is, I sin hyperbolic y, I can write it as a sin I y. Okay, now what we can do, this minus sign as it is, this is sin a cos b plus cos a sin b, so which is nothing but sin a plus b, that is x plus I y. Okay, so now this is what we are getting, minus of sin x plus iy is nothing but z, so this is f dash of z. Okay, now what we are going to do, we need to integrate this f dash of z with respect to z, means I am going to get what, f of z is equals to integration of this sine, what we are going to get, cos z, that is minus cos z, integration of sine is minus cos z, so minus of this minus, what we are going to get, plus cos z plus integral constant c we have to write with this, so that is f of z is equals to what we are getting, cos z plus c. This is the required analytical function. This is how we can construct. Okay, thank you.